Today we'll be going over Unit 1.6, which is Photoelectron Spectroscopy. This is abbreviated as PES. Typically on the AP exam, you're just asked to interpret the PES data, but we will go in a little bit to how they actually get that data, which can help you understand how this works. So we looked at an image like this in the 1.5 notes. There's kind of a few unexplained problems with this model that you might notice. So there are things that don't follow the trend that we established based on the shell model. So if you look at the first ionization energy for the third element boron in the second row of the periodic table, it's about 800 kilojoules per mole. And it's less than the energy of the second element beryllium, which is 899.4 kilojoules per mole. So you can see right here, this is that little bump right there. So we would expect it to follow the trend and be a straight line, but you can see that it is less than expected. Same thing over here when we look at aluminum and magnesium. The first ionization energy for aluminum is 577 kilojoules per mole, whereas magnesium, right there, is 737 kilojoules per mole. So those don't follow the trends that we had expected based on the shell model. So PES data kind of helps to explain this a little bit. So let's revisit the shell model a little bit. We can see that the first row has 2 elements and n equals 1 can hold 2 electrons. Second row has 8 elements and n equals 2 can hold 8 electrons. The third has 8 elements and n equals 3 can hold at least 8 electrons. But we actually know that 18 electrons can be held based on the data we saw in the last section, 1.5. And just a reminder, with the shell model, we do have inner core electrons that shield valence electrons in the outer shell because they are all negatively charged and likes repulse likes. So photoelectron spectroscopy is an experiment where we have high energy electrons removing electrons from any shell, not just the outer shell. So the electrons that are ejected with a higher velocity experience less acceleration towards the positive plate in the magnetic field. The location where the electrons strike the electrostatic analyzer in this machine is used to determine the velocity. Kinetic energy of the electron can be calculated using the equation kinetic energy Ke equals 1/2 mass times velocity squared. So only one electron is removed from each atom, but again, that electron can come from any shell. Removing a second electron from an atom wouldn't give useful data because it would require much more energy than removing the first. And we will talk about this a little bit more when we talk about periodic trends. When the photon absorbs the electron, it's provided with the energy required to be ejected from the atom, which is the ionization energy, and the kinetic energy associated with its transitional velocity after it has left the atom. The ionization energy for each ejected electron can be calculated by subtracting the kinetic energy of the ejected electron from the energy contained by the photon, which is h times the photon's frequency. So ionization energy is calculated, Planck's constant times frequency again, minus the kinetic energy of the electron. So this is a little image of this analyzer, kind of what happens. So we have a magnetic field, a beam of atoms that is basically struck with a bunch of photons, typically X-rays or UV lights. Then electrons are ejected. There's a magnetic field, so the negative will repulse electrons, positive will attract them. Slower electrons will be more attracted, so they will curve more, and faster electrons will be moved less so because they are moving so fast through the magnetic field. Then there's an analyzer over here that basically determines the location at which it strikes. That location can be used to figure out the energy of the electron. We do have a POGL that goes into this that I think explains it really well. And that'll probably make more sense now. I know this just sounds like a bunch of spiel and stuff, but this will make more sense once we go through the POGL. It explains this process very well. And I know it's a lot to grasp right now, so if you don't completely understand this process, once we do the POGIL, that should help a lot, okay? So next we're going to focus on talking about the output, which is really what the AP test kind of focuses on anyway. So when we get a spectra out of this PES, we have elements here: hydrogen, helium, lithium, beryllium, and boron, okay? So this is the PES data for hydrogen, helium, lithium, beryllium, and boron. The ionization energy on these graphs increases from right to left, so that's in the way, but you'll notice that the x-axis is actually flipped. Usually we expect the smaller number to be on the left and the bigger number to be on the right. For PES data, this is typically flipped, so just keep that in mind. So higher energy is actually to the left, not to the right. So hydrogen only has 1 electron, so its peak is half as tall for that of helium. So the peak, or the height of the peak, corresponds to the number of electrons with that ionization energy. So that is why hydrogen's peak is half the height of helium's peak. It has twice as many electrons in helium than we do in hydrogen. In lithium, we still have 2 electrons in the 1s shell, and then we have 1 electron in the 2s shell. The ionization energy for n equals 2 is much less than that of n equals 1 because it's further than the nucleus and it's shielded by inner core electrons. So this ionization energy is much smaller than this one. For beryllium, we have 2 electrons in 1s and 2 in 2s. So notice these are the same heights. They both have 2 electrons that correspond with that peak. Again, the ionization energy of this one is much less than the ionization energy of this one here. Notice that the ionization energies for n equals 1 and n equals 2 increase as more protons are added to the nucleus. So you'll see that they increase, even though all of these are 1s, the ionization energy is increasing. This can be explained through Coulomb's law because Q, or the magnitude of charge, is increasing in the numerator each time a proton is added. For boron here, we see 3 peaks. From our data on first ionization energies, we assume that n equals 2 could hold up to 8 electrons that would have the same ionization energies because they would be the same distance from the nucleus, based on the shell model. But PES data, photoelectron spectroscopy, tells us that the shell model has to be revised. So we see that the n equals 2 shell contain 2 subshells with different ionization energies. So this is why the first ionization energy of boron is slightly less than that of beryllium. Okay, so you can see that 0.8 here is less than the 0.9. So basically, we know that boron is in period 2. It's the third element in period 2. And based on the shell model, we would expect only 2 peaks here. But this shows that there must be subshells within the 2 n equals 2 energy level. So this is where we were like, okay, shell model isn't perfect. There are limitations, and that's why we got data to do another model. But here we have, again, more data for carbon, nitrogen, oxygen, fluorine, and neon. So the same trend can be seen in these elements as the ones that we just saw. They all have 3 peaks that indicate that there are 2 subshells within the n equals 2 shell. We can see the first and second peaks indicate the presence of 2 electrons based on their heights. For carbon, the third peak has 2 electrons, but if you look for nitrogen, the third peak has 3 electrons, so it's even taller than the 2 electron peaks. For oxygen, the third has 4, fluorine 5, and neon 6. So remember, the heights of these peaks tell us the number of electrons within that ionization energy peak. So the PES data shows us that n equals 1 can hold up to 2 electrons, n equals 2 can hold up to 2 electrons in the second subshell, in the first subshell, but up to 6 in the second subshell. So this first 2s here can hold 2, and then what we come to describe as 2p can hold up to 6. So this kind of recaps that, and this is a slide that we did see in the last presentation. 1s can hold maximum 2, 2s can hold 2, while 2p can hold 6, so n equals 2 can hold a total of 8 within its 2 subshells. And then n equals 3 contains 3 subshells and can hold a total of 18, 2 in 3s, 6 in 3p, and 10 in 3d. This chart is ionization energies calculated in megajoules per mole, and this is all obtained from PES data. So electrons from 1s to sodium has 4 peaks in the PES spectrum, 1, 2, 3, and 4. Each of those peaks correspond to a subshell, 1s, 2s, 2p, and 3s. Magnesium also has 4 peaks, same subshells here. If we have the PES graph, the 4th peak for magnesium would be twice as tall as that for sodium because it contains 2 electrons, whereas sodium only contains 1. Aluminum and argon both have 5 peaks, aluminum, argon. Potassium and calcium have 6, scandium has 7, and evidence from other forms of spectroscopy suggests that the last electron in scandium is n equals 3, not n equals 4, which shows us that the 3d subshell falls kind of after the 4. So this gap here, where we get 3d, we didn't have it before, so it's filled after 4s, but it corresponds with the energy level n equals 3, not n equals 4. So that's how they knew that 3d is filled after 4s. 3d is filled after 4s. So after seeing this data, hopefully you see that the shell model wasn't perfect. It didn't describe everything and explain this data. So shell models showed that all electrons within a given shell are at the same energy level, whereas PES data shows that there are 2 subshells in n equals 2 and 3 equals in n equals 3. There is a model that provides a better explanation, and that of course is the quantum mechanical model. So PES data suggested a need to refine the shell model. The spectra don't support the shell model because they show that there are different energies within the n equals 2, which is why they came up with the subshells. The quantum mechanical model can be used to explain why there are 2 subshells in the n equals 2. According to the quantum mechanical model, n equals 2 contains 2s, which can hold up to 2 electrons, and 3 2p orbitals, which each can hold 2 electrons, for a total of 8 electrons in n equals 2. All electrons in 2p are at the same quantized energy level, so they correspond to the same peak. So mostly on the AP exam, you are interpreting these PES models, these outputs, and you can connect the PES data with different elements on the periodic table based on the quantum mechanical model and orbital diagrams that we build with atoms. Okay, so that is unit 1.6. Let me know if you have any questions.